We're currently experiencing one of the greatest warmings that the Earth has ever seen, and it's going to alter everything about how we live. It's going to change sea level. It's going to alter the locations where we can live. It's going to alter precipitation patterns and where we can grow crops and where different species live. And in order to be able to predict where we're going and to either adapt to that or to try to mitigate it, we need to have an understanding of what that path is. My name is Meredith Kelly. I'm an associate professor in earth sciences at Dartmouth College, and I've been here for about 12 years. I have an incredible lab. I have a really supportive department that facilitates and encourages my work, and I get to teach incredible students. The main goal of my research is to understand how and why climate has changed in the past. And there are a number of reasons why I'm interested in that. First is just, it's fascinating how Earth's climate system works. It has many, many different components, and it's incredible to learn about it. Second is that what we're experiencing right now is climate change, and a lot of that currently is influenced by processes that humans are doing to the environment. But there's also natural climate change going on. And in order to make accurate predictions of future climate conditions, we need to understand both. For example, people had thought that climate changes slowly and on a sort of sinusoidal pattern of warming and then cooling, these interglacial and glacial cycles. But what was shown by the Greenland Ice Core records is that climate actually can change really abruptly and drastically. So there were observations of climate changing on the order of decades, huge magnitude temperature changes, 10 to 15 degrees C. And if it happened today, it would really significantly impact humans. That is on the order of a human lifespan, right? So that's different from changes that happen over tens to hundreds of thousands of years. That was so fascinating to me. It really turned on its head what scientists had thought about how climate changes, and it showed that climate behaves in a way that we really don't understand. For my research in Greenland, the primary goal is to reconstruct the full extent of a glacier at a certain time and be able to tell that time. Before even we go into the field, we use remote imagery. And the remote imagery that's available now between satellite imagery and LiDAR imagery is incredible to be able to read the signature of a landscape and tell where a glacier was in the past based on the landforms that it produces or the erosional features that it produces. The next challenge is trying to actually determine the age of that, because we want to compare that piece of evidence with evidence from elsewhere, and in order to do that, we have to have a similar scale on which to do that. That's usually time. And so I have an incredible method to do that. It's called cosmogenic nuclide surface exposure dating. It's actually just taking a rock that was set down by a glacier, and then I can bring that rock back to my lab here at Dartmouth and extracting nuclide from that rock. So I can use how much of that nuclide is in the rock to tell how long that rock has been exposed to the atmosphere. And I can essentially date the exposure of that surface. That's what many of my graduate students and undergraduate students have been involved in, is developing the ages of different glacial features. In looking for an academic job, I always was hoping to find a job in a place that was in a location that was formerly glaciated. And the main reason for that is because I really like to teach in the field. And if I was in a place like, for example, in the southern United States or something that hadn't been glaciated, I wouldn't be able to do that as easily with some of the classes that I really like to teach. But I can do that at Dartmouth. And I literally take my classes out to the green and can talk about the glacial history and the climate history of the green, which to me is so much fun. When I get my students out here, my first question for them is, what does this landscape look like? Is it natural? Can we tell something about the past from looking at the landscape? And they look around and they see Baker Tower, they see Collis, they see, they walk to class every day. And I say, no, forget about that. What I really want you to look at is the landscape. It's this incredibly flat feature. And we're sitting on this plain that's above the river today. And what we come to after a discussion is that this feature right here was the floor of a lake at the end of the last ice age. And that lake occurred because the ice sheet retreated north of Hanover, and there was a dam in the Connecticut River Valley that caused a big lake to form. And so Hanover was underwater. If they would have been walking to class 14,000 years ago, they would have been walking at the bottom of a huge glacial lake. The other really interesting thing about the records in Hanover and in New England is that we can look at the influence of these rapid climate changes on an ice sheet. So we can look at when climate got warmed, what happened with that ice sheet? And that's a huge question today is, if we have a rapid climate change, or if we're having this rapid warming that we're seeing now, what's the response to that ice sheet going to be? We have the best analog for that right here under our feet. One of the largest rapid climate events is something that's known as the Younger Dryas, and that is about a 1,200-year long event that happened between 12,900 and 11,700 years ago. And basically what was happening, that was the end of the last ice age. And climate was warming, the large ice sheets that were in the northern hemisphere were shrinking, the big ice sheet that was over in New Hampshire had melted. The ice sheet was actually 12,900 years ago. The ice sheet was just north of the Canadian border where we are here. So, so there was still an ice sheet in North America, but Hanover was unlocked at that point. And then all of a sudden, there was a rapid cooling that lasted for 1,200 years ago and basically put the Earth, at least the northern hemisphere, back into cold ice age conditions. And there are a lot of questions about how and why that happened. I'm standing here at Occam Pond, and this pond is incredible. Through my teaching and through my research with students, we've obtained sediments from the bottom of the pond, and we've determined that the bottommost sediments in Occam Pond are as old as 13,000 years old. And the sediments on top of them preserve a record of the environmental and climate history of Hanover, New Hampshire throughout this time. And we've been able to look at times such as during the Younger Dryas, or during times when there was warming during the current interglacial, and look at how those climate changes have influenced the Hanover area in particular. A large part of my research focuses on understanding past climate through using glaciers in the tropics. And I often say this on the first day when I'm teaching my large intro class, I say, well, I work on glaciers in the tropics. And students say, what? And then I say, well, where do you think there are glaciers in the tropics? Where do you have to go in the tropics for it to be cold? And so I work way high up in the mountains in the tropics. From where the road ends at about 4,800 meters above sea level, we walk to about 5,200 meters above sea level and set up camp. And it's hard, that's high. It's cold, the air is very thin, but we work, we do our mapping, we collect rock samples, we obtain sediment cores from lakes. I've worked pretty extensively in Peru, and I have a large ongoing project in Uganda, and I'm starting a new project in Colombia. When I look at the Earth's climate system, the biggest part of the Earth that I see is the tropics. The tropics receive the most sunlight on Earth. They're essentially the heat engine of Earth. There's a huge amount of energy and water vapor production there. And right now, in today's world, they are the largest driver of interannual climate variability, and that is the El Niño Southern Oscillation. Yet, they're never called upon in terms of past climate drivers. And I always thought that was curious. So one of my goals over the past 10 years has been to develop more temperature records from the tropics. And again, we don't have thermometers out 10,000 years ago, so let's look at how glaciers have changed in the past, right? Glacier is small, it was probably warm. Glaciers are big, it was cold. Same holds true in the tropics. And so we've applied very similar methodologies there, reconstructing past mountain glacier extents using geological mapping, applying the surface dating technique that I can do, looking for any kind of organic material coming out of the glaciers, and also obtaining lake sediments from nearby lakes. Another component that we've added in more recently to this is using glacier modeling. So having actually a numerical model of the glacier that we can build based on a digital elevation model of the land surface and our understanding of ice physics. And then that can really help us get quantitative information about things like precipitation and temperature and the lapse rate that all contributed to a certain glacier extent. For anybody who hasn't been on a glacier ever, it's a pretty incredible experience. Mostly I work along the margin of a glacier, along the edge, but sometimes we get the opportunity to go up and walk on the glacier, and there are curious things that we like to look at on glaciers. It's a pretty powerful experience, particularly now when all of the ice margins that I've been near are just retreating drastically. There's so much going on. There's so many different processes going on, right? There's like a wall of ice, but then there's sediment and rocks in that ice. And then there's just water coming down everywhere. And there's streams on the ice, and then there's maybe a lake in front of the ice, or there's streams coming into the sediment in front of the ice, and everything's moving. Nothing is settled. The meltwater from those set up ecosystems in the mountains around the world, right? They provide fresh water for people. They provide a way of life in places, and losing those I feel like, is catastrophic. The ice sheets, to me, are the real scary thing, though, because we really don't understand how ice sheets behave. Like, when we start to melt these large ice sheets, will they stop? Are they going to enter some dynamic stage where we can't turn off that ice retreat? So in the past, at least in the recent past, we haven't gotten there. Those ice sheets have stayed around, at least through our sort of current interglacial. And scientists are now really investigating, looking at the last time the Earth was in an interglacial climate and how the ice sheets reacted to that climate. And this evidence of having abrupt climate changes in the past is scary, right? The climate system could have a feedback that we don't know about, that we don't understand yet, that could just alter the direction of where we're going or be very unpredictable and hard to adapt to. I feel like my research contributes to an understanding of climate change and an improvement, I hope, in the predictions of our future path of climate. But I think perhaps my greatest contribution to understanding climate and making the world a better place in terms of climate change is through teaching at Dartmouth. I teach classes that are focused on climate. They're grounded in geology and the record of the past, being in an earth sciences department, but I really strive to provide the Dartmouth students who are in my classes with a good understanding of how climate change happens on a physical basis. What are the main drivers of climate change, natural climate change and human-driven climate change, so that they can be educated in their future decision-making, in their voting, and their lifestyles. And so I think, to me, that Dartmouth has provided me an incredible opportunity to do that.